Well, say hello to everyone. So we've been talking about ways to get around the problem of vibration when we're doing phase shifting interferometry. And in the last class, we talked about a system where we would measure the vibration and then feed that back into the system to introduce another vibration or a changing of the phase to cancel out the effect of the vibration. And the system worked quite well. We saw some results for it, but it was rather complicated and expensive, difficult to build. So let's look at some other ways of solving the vibration problem. One technique that a few people have used is what's called spatial synchronous. Other people have used what's called a Fourier technique. These two techniques are really so similar, I've decided that when I talk about them, I will combine them into one section here. Both of these techniques involve using only a single interferogram, but the interferogram has a lot of tilt, and that's probably one of the major problems with it. So we're going to introduce a lot of tilt. So we can write the irradiance of the interference pattern as some number times another number plus, well, some number times 1 plus another number times the cosine of the phase difference between the two beams. And we're going to write, well, we have the phi of xy, and that's what we want to determine. What is phi of xy? And we've put in a lot of tilt fringes. And so I'm just going to, write the tilt as 2 pi f, which is some number, times x here. So a lot of tilt in the x direction. When I talk about a lot of tilt, it might be 100 fringes or something like that. So now we're going to detect this by our detector array and get this data in the computer. And then in the computer, I'm going to take this irradiance pattern with the numbers for it and multiply by cosine of 2 pi fx and multiply by the sine of 2 pi fx. So simply taking this expression here, multiplying by the cosine of 2 pi fx, and again multiplying it by the sine of 2 pi fx. And when we do this product, what we will get will be a sum and a difference. And so we're going to get something. It's going to go where we have the 1, we're going to get just a cosine of 2 pi fx. And where we had the cosine function here, we're going to get the difference term would just be cosine of phi. And the sum term would be cosine of phi plus 4 pi fx. Now, if this were not exactly, the 2 pi fx were not exactly the same as what we have here, we would still get the difference and the sum. The sum wouldn't be quite 4 pi fx, but it would be close to that. And the difference here would have a little bit of something left in the that goes as x, depending on the difference between the two signals here. And when we multiply by the sine, we get a similar term, a similar expression here. Of course, we get the sine of 2 pi fx. And then we get the difference term, which is now going to be a sine of phi. And we get this term here, which is a sum term that has the 4 pi fx in it. So, of this right here, what's important, or what's of interest to us, is the low frequency term, namely the term that has the phi in it, the cosine of the phi and the sine of the phi. And so we can take these two terms out, and we'll call one S1, that's the cosine, and S2, that's the sine, and then we simply take minus S2 over S1, and we end up with the sine of the phase divided by the cosine of the phase, hence the tangent of the phase. So that's looking only at the low frequency terms. The high frequency terms here, we're going to some way filter out in the software, or sometimes people do this electronically, but we'll filter out the high frequency term and then the really high frequency term over here, and we're left just with a sine and a cosine. Now, as I said before, if the tilt here is a little bit different, so the 2 pi fx there is a little bit different from what we multiply by here, the cosine of 2 pi fx and sine of 2 pi fx. The only effect of that will be that the different signals will be a little bit different, and we'll end up with a little tilt in the final calculation here. Okay, so any questions on that? So maybe there are two things that are a little bit, give us a little bit of trouble. The first is that when we do this filtering to pick out just a low frequency term, we're smoothing the data a little bit by doing the filtering. But the bigger problem is that we had to introduce a lot of tilt in the interferometer in order to get this term. And as I said, you might have 100 fringes, maybe 200 fringes or so. And so the amount of tilt that you have, you might get some additional aberrations in the interferometer from this, the beams going off axis back through the interferometer. Okay. So that's what we call spatial synchronous. The Fourier method is really essentially the same thing. We start off again with a lot of tilt. So a lot of tilt fringes here. Phi again, what we're trying to measure. And I just wrote the cosine as e to the I phase plus e to the minus I phase. So when I take a Fourier transform of this, I'm going to get a DC term. I'm going to get a first order. I'm going to get a minus 1 order. So this information, interferogram data, goes into the computer. We take a Fourier transform. So this is the interferogram data. The phi of xy will cause these fringes to not be perfectly straight and equally spaced. We take the Fourier transform of that. We get the 0 order. And we get a +1 order and a -1 order. So now we spatially filter once again. In this case, we spatially filter to select out the +1 order, and then we do an inverse Fourier transform to get the wavefront back. So this is, say, the +1 order. This 2 pi fx is the tilt, and that causes it to separate from the 0 order. And when we then take the inverse Fourier transform of that, we're just simply going to get the phi back again. Now you see some ringing around the edge. You generally get that because of the filtering process. You get a little ringing around the edge. The filtering process, you smooth the data a little bit. And once again, the requirement for having large tilt is going to limit the accuracy of the measurement. So these two techniques, the spatial synchronous and the Fourier transform method, have been used by a number of people. There's at least one commercial instrument out now based upon this. And I mean, it works fairly well. But you do have ringing at the edges. You do have some smoothing of the data. And the bigger problem is the large tilt going through the interferometer. You probably pick up some aberrations you don't want. What people do sometimes is they repeat this with tilt in the x direction, plus or minus x direction, and tilt in the plus or minus y direction. And from that, from these 4 measurements, you can pick out some of the errors that you're getting by sending the beams through the interferometer off axis. But you can't get rid of all of the errors. Maybe you can get it down to an acceptable value by doing these additional computations. Depends a little bit on the interferometer that you're using. So any questions on this?
When there is closed fringe.
Can't do closed fringes are not going to work. You have to put in tilt. There has to be enough tilt here to separate the orders. And I mean it's not quite so obvious here, but it's the same story here because you have the high frequency, and then you have a frequency it's not quite so high, and then you have the low frequency. You have to be able to separate these. So there has to be enough tilt to essentially separate the orders. So it would not work for closed fringes. Any other questions? Okay. Now, this is maybe becoming a little more interesting nowadays as you're getting detectors with more detector points. So you can put in more tilt fringes to do a better job of separating the orders. But again, you have the problem that the way I look at it, you're really misaligning the interferometer just to get the data. And I don't know, that bothers me a little bit. Okay, so that's interesting. The next technique also requires tilt, but maybe not as much tilt. And this is what we call the spatial carrier technique. And this has been around for quite a while, but it's maybe used more now than it was 5 years ago. Again, maybe because we're getting detectors with more pixels, it's become a little more practical. So in this case, what we're doing, we're introducing enough tilt so between detector elements, these little rectangles here are supposed to identify detector elements. So between detector elements, the phase changes by 90 degrees. And so what we have then is we will have 90-degree phase shifts between adjacent pixels. So if I look here, as I go one cycle here, I have 1, 2, 3, 4 detector elements. And then what we'll do, we'll take the intensity behind here, intensity behind there, and behind there, and use these as our 4 phase-shifted frames. And so we had to introduce enough tilt to get a 90-degree phase shift between pixels. We also, that the slope of this wavefront can't be varying so fast to cause too large of a phase difference in the beam over 4 pixels. And we're doing kind of a smoothing of the data again because we're finding, we're using 4 pixels to find the phase. Now we're not really smoothing it by a factor of 4, because what we would probably do, we'd use first 4 pixels to get one data point, then we jump over 1 pixel and now use pixel 2 through 5 for the next data point, 3 through 6 for the next one, and so on. But there is some smoothing of the data. There is some restrictions on what the slope of the wavefront can be. Any questions on the basic idea behind this? I'm going to talk a little bit more about it, but I want to make sure you understand the basic idea. Okay. So how do we create this carrier frequency? Well, I mean, one is you can just tilt the reference beam and create it that way. I hate doing things. I hate putting too much tilt in, though, because you always get some aberrations with a beam going through the interferometer off axis. But I will show some results for doing this first approach, but it's not my favorite, I guess I'd have to say. The second is where you can put a Wollaston prism in the output to get, well, if the test and reference beams have orthogonal polarization, I can put a Wollaston prism in the output to get the tilt. And I'll show a slide of that in just a second. And the last approach here is going to be my favorite approach, but it's going to be using a pixelated array in front of the detector. And I'll get to that, but it's going to be a few slides away before I get to that. So Wollaston prism and the output beam. So what we could do, instead of introducing a lot of tilt between the reference and test beams in the interferometer, we can have the reference and test beams parallel in the interferometer if they have orthogonal polarization. And then in the output here, we put in a Wollaston prism. And so one polarization, we'll see one refractive index, and the orthogonal polarization, we'll see a different refractive index. And the end result is that the two beams, test and reference, having orthogonal polarization, will leave the Wollaston prism at a slightly different angle. And if I now put in a polarizer, I will have the interference of these two beams at some angle to each other. And if I pick the right Wollaston prism here, I can make it so the fringe spacing is just such that we have 4 detectors per fringe. And so the advantage here is that inside the interferometer, the test and reference beams are not tilted with respect to each other. But it does have to be an interferometer where you can have the test and reference beams have orthogonal polarization. So we've played around with this technique a lot. Even here, you run into a little bit of trouble in that these two beams, when they leave the Wollaston, they are sheared a little bit with respect to each other. Not very much, mind you, very, very little. But sometimes it's even enough shear that you'll pick up some aberrations that you didn't want. This generally comes from the fact that the collimated beam going into the interferometer is probably not a perfectly collimated beam, has some aberrations, and you end up, you say, well, errors in that collimated beam don't bother you because they will be present in both the test and reference beams. But if you have just a little bit of shear between the test and reference, which we'll get here, then you will see that difference. Okay? So I want to show 2 examples of using this technique, spatial carrier technique, in an interferometer. And these are 2 examples that we have done at 4D technology. The 2 examples, the first one I'm going to talk about will be an interferometer that worked at a wavelength of 193 nanometers, and that was for lithographic optics, testing of deep UV lithographic optics. And the other one is something we did very recently of a high-speed interferometer working at between 500 and 1400 frames per second, and I'm going to show some results for down in the 500 frame per second. So this first interferometer is just the only thing that's really unique about it is the wavelength here, 193 nanometers. It's going to be a Fizeau type interferometer and using the spatial carrier technique. And the idea here is, here's our laser, 193 nanometers. Fizeau type interferometer, testing some optics. I show it just for testing a flat, but is used for testing a lot of other different optics besides that. And in this case, we got the tilt between the 2 beams by just tilting the reference surface. And so we had to have some very good optics back here because the test and reference are going back through this lens at different angles, off this beam splitter, again at different angles, and coming down here to where we're looking at the interference fringes. And so in this case we put in enough tilt, so if I look at put it in at an angle here. And so we had phase that went as 0, pi over 2, pi, and minus pi over 2. And so if and so this would repeat itself over the camera. And so if I took, well, I could think of this as groups here of pixels. If I took all the ones corresponding to the pi, we get an interferogram look like that. All those corresponding to minus pi over 2 would get this, and so on. And instead of using a 2 by 2, we actually used a 3 by 3. And so we used a 9 frame algorithm here, and I'll show the equation for it in a second. But you can think of these phase shifts as just giving us a bunch of sines and cosines here. And so you would pick the ones that gives you the sines and the ones that give you the cosines out of here, and you get the tangent of the phase as we've seen before. So this system, in spite of the fact we're doing something I hate doing, sending the beams back through the interferometer at different angles, we did take enough care in producing the optics here that we were able to get quite good measurements of an uncalibrated accuracy of 1.8 nanometers RMS, and RMS repeatability turned out to be 0.07 nanometers RMS. So this spatial carrier technique actually worked pretty well in this particular case. The next interferometer I want to show is something we did quite recently here. Again, using spatial carrier. Again, using a setup that looked pretty much like this, except this had a visible wavelength laser in it, and had a high-speed camera here. So you're getting everything in one frame, so that's nice. So it works well in the presence of vibration. And this particular camera we could read out at different frame rates depending upon how many pixels we were using. And the results I'm going to show will be for the 525 frames per second and about 880 by 880 pixels. So the first, I'm going to show some movies here that were taken at this high speed. And the first movie I'm going to show will just be taking a jet of air and blowing the air into the beam. And so you can see the air coming in. Again, this is at 525 frames per second. So when the air comes in, you can see the leading edge on it, and track it as it goes through. The purpose of this was not to measure index variations caused by air streams, but it gave such a pretty picture we had to take a picture of it. The next one, it's kind of neat. We took a cup of water and we dropped some alcohol in it, and had a little vibration present. And so this is looking at the fringes from just reflecting the light off of the water in the cup. And again, reading it out at 525 frames per second. Every now and then you'll see these bubbles here, which is the alcohol, I think. There was a little alcohol dropped in here, and when that comes up to the surface, you see a little bubble. So anyway, we're doing a lot of frames per second here, and now we're going to measure using phase shifting, we'll measure the height variations of the surface of the water. Anyway, this was kind of playing with it. The real optics this was made to test, I can't show you, unfortunately, because they didn't have permission from the customer to show the results for that. But anyway, this gives you an idea of what you can do using the spatial carrier approach. And it's not a bad way for getting around the effects of vibration. Again, the thing I probably don't like about it is the large angle between the two interfering beams. The optics have to be really good to or else some way you have to calibrate out the errors in the optics that arise because you're sending the beam through at different angles. So any questions on this? Okay. So this is another way of measuring phase difference between the two beams, where we're going to capture all 4 phase shifted frames at once. This is a rather complicated way, but it works. So let's start off here with a laser that output has linear polarization. And we're going to send that through a half-wave plate. So I can rotate the half-wave plate to change the angle of polarization here to essentially vary how much light I have in horizontal polarization compared to how much I have vertically. And then I just go to a regular beam splitter here, not a polarization beam splitter in this case, just a regular beam splitter. And part of the beam will go to the test, whatever I'm testing. I'll just show a flat mirror here. And part of the beam will go to the reference up here and back. So these 2 beams come out of here. Fine. And I will now put in a polarization beam splitter. So this will reflect one polarization. Let's say the polarization perpendicular to the screen here. And it's going to transmit the orthogonal polarization. Now, what I didn't mention, is up here I have an 8th wave plate oriented with one of the axes at 0 degrees. And I'm going to go through that 8th wave plate twice. So it's going to act like a quarter wave plate. So if I think here for a second, for the light in the reference beam, I think this is actually pretty clever, the way this works. For the light in the reference beam, I have light polarized at some angle. Well, I'll just say 45 degrees, but it doesn't have to be 45 degrees. But I have some component in the horizontal direction and a component in the vertical direction. And what this is doing is introducing, going through an 8th wave plate twice, or a quarter wave plate, I'm introducing a 90-degree phase shift between the light with horizontal polarization and the light with vertical polarization. And now, down here, I put in a polarization beam splitter, and I'm getting 2 interferograms here, but these 2 interferograms will be 90 degrees out of phase because of this 8th wave plate back here. Isn't that kind of neat, the way that works? I remember the first time I read about this, I thought, oh, that's a really clever idea there. So I have 2 interferograms here with 90 degrees out of phase. I want to have 3 or 4, but so far I've only gotten 2. Okay, any questions up to this point? Because I have to warn you, I love this technique, so watch out for exam questions. Okay, so now I have 2 of my, well, I'm going to try to get 4 phase shifted frames. I have 2 of the 4. Where do I get the other 2? Well, the other 2 are going to come back here. And we already said that in class before that, whatever interferogram I get here, if this is a dielectric beam splitter, going back towards the source, I have an interferogram which will be 180 degrees out of phase. Let me go ahead to a view graph and one slide ahead, and then I'll come back to this. So where does that 180 degree phase shift come from? And we talked about this before, but I want to show a slide of it here. So this is our beam splitter. So I'm just looking at this beam splitter right here, dielectric beam splitter. A beam comes in here, and the beam that goes over here will come right back on itself. The beam that is reflected from here will go up here, went from a low index to a high index, comes down here again, low index to high index again. So if I'm getting a 180-degree phase shift, I'm getting it twice, so it's 360, so it doesn't bother me. If I look at the output here, let's see, this is reflected from low to high, comes out. This beam is reflected from high index to low index, comes out. So I do indeed, if I look at these two interferograms here, they will be out of phase by 180 degrees, as long as this is a dielectric beam splitter. Okay, buy that? Any questions on it? So now I go back here, and I take that beam coming back. I just put in a regular beam splitter here. I put in here another polarization beam splitter, and I'm going to get the same patterns I got here, except for that 180 degree phase shift. So I have 0, 90, 180, 270. So these four outputs, which I get all at the same time, give me my four phase shifted frames all at once. So this would work, at least in principle, this is going to work very well in the presence of vibration. And in last class, when I was talking about this technique where we were, well, let me go back to it, a few slides back, many slides back. When I talked about this phase sensor here, what we used for that phase sensor was that device we just looked at. But we were measuring the phase only at a single point. And so it wasn't a real complicated, maybe more complicated than one, but it wasn't real complicated and it worked well. But what we could do, if I was really ambitious, get to the right page here. What I could do here is to have 4 CCD arrays here. And I could get, and say, I could have a 1K by 1K element CCD in each of these 4 positions. And I could be measuring the phase distribution across the beam, not just at a point, but at a million points, all at once. I'm getting all four phase shifted frames at once. And people have built phase shifting interferometers like this. The problem is you have 4 detectors. Probably these detectors have different response. They probably have different noise associated with them. And you're going to have to align the 4 detectors just right. So pixel number 1 here sees the same part of the test beam as pixel number 1 here, and 1 there, and 1 there, and so on. So the alignment of these detectors and the calibration of the detector arrays can be difficult. So while on paper, this looks like a great way of doing phase shifting in the presence of vibration, in practice it's difficult. Not impossible. Interferometers like this have been made and sold, but probably only 3 or 4 of them, I think, because it ends up being hard to calibrate and hard to keep in calibration. But I think from a technical viewpoint, I think this is very clever. I like it very much. From an academic viewpoint, I guess I'll say I like it very much. So any questions on it? Okay. Well, we're finally getting to what I really like here. And thinking of what we just did kind of leads us to what we're going to see here. And this is what we're going to call a single-shot holographic polarization dynamic interferometer. So what a name, what a name. And the way this works is the following. I'm going to start off, I'm going to show it for the Twyman green. It can work with a Fizeau as well, but Twyman green is kind of easier, certainly easier to describe and easier to build, in fact. Polarization beam splitter that we've seen before many times. Quarter wave plates that we've seen before. Testing, say, a spherical mirror. So, as we've seen many times before, coming back here we have a test and reference beam that has orthogonal polarization. Out in here, what we're going to have is a holographic element. And typically these are made on a computer and then constructed using electron beam recorder. This holographic element is going to, if you send in one beam, you're going to get 4 beams coming out, the way it's produced. So if I send in a test and reference beam having orthogonal polarization, I'll get 4 samples of that coming out. I'll get, test and reference here, test and reference there, down there, and down there. And again, test and reference are orthogonal, so they don't interfere yet. Here's our detector array. Right in front of the detector array, I'm going to put in a phase mask. Going to be 4 birefringent elements. And typically, you might use mica here. That will introduce a phase difference between the 2 orthogonal polarizations. So it will introduce a phase difference between the test and reference beams. And we're going to make that phase difference so in one quadrant here, it's 0. In one it's 90, one it's 180, and the other one is 270. So test and reference is still orthogonal, so we still don't, orthogonal polarization, so we don't see any interference. So right after this phase mask, we're going to put in a polarizer at 45 degrees. So falling on our detector here, we're going to have 4 phase shifted frames, differing by 0, 90, 180, 270. And so I'm capturing all 4 frames at once. Unlike the previous example, in this case, all 4 of these are falling on one CCD array. So the alignment is not so bad. The calibration of the array is not so bad. And we can actually get pretty good data out of this. So what we have here is that we have, if I have vibration, we have these fringes jumping around like crazy. But there's a fixed phase relationship between them determined by these 4 birefringent plates. And as long as I have enough light that I can make a short enough exposure time to essentially freeze the vibration, I can make good measurements in the presence of vibration. And if I have air turbulence, then what I'm going to do is to do the measurement many, many times and average the results and average out the effect of the air turbulence. So I love this little system here. And any questions on how it works? Well, the story that goes with this that I often tell is that I've told you before in class that Leica, we sold a lot of interferometers. Vibration was always a problem, though. And so after selling Leica and coming back to the university, I decided some way we were going to solve this vibration problem. And we looked at many different techniques for doing that. And I have to say we got some interesting papers out of that. But we never came up with anything that really was what I would call could be made into a commercial product. And then I heard about this system here that two people in California had invented, and they had started a company. And James Millard and Neil Brock were the names of the two people. So I went over to see this, and I was just, I mean, it was one of the biggest days of my life. I mean, it was so fantastic what I saw. You'd set up the interferometer on a table like this. You know, on another table on the other side of the room, you'd have whatever it is you're testing. No vibration isolation at all. And it did wonderful measurements. And I just, you know, it's what I've been dreaming about for years. So I had to have it. And so when we went to lunch, I made an offer to buy the company. Fortunately, it was only a two-person company, so it wasn't a lot of money. I ended up buying it, and we moved it to Tucson here. And it's called 4D Technology now. And so we made interferometers like this. And, you know, you can use it for testing of large optics. This is a case of up at Ball Aerospace where you have a large environmental chamber. And it's hard to put the interferometer inside the chamber. And when you have it outside the chamber, you have all kinds of vibration problems. But with this type of system, it works very, very well in the presence of vibration. Or here's a case up in Wales where they have a computer-controlled polishing machine. And so they want to polish a while and then test it. And without vibration isolation. And so here's the interferometer sitting up here looking down at the part. And that works very well. So you can very easily do measurements in the presence of vibration. You know, mirror interferometer can be on separate tables. You can average out the effects of air turbulence, and it works very well. So this system, as I said, is vibration insensitive. It gives you measurements down in the nanometer range. You could make measurements of surface height. I haven't shown it here, but you can make phase movies. I'll show some phase movies in a little while. And so it's pretty nice, but after we got working with it, I realized as nice as it was, and as much as I loved it, it wasn't perfect yet. And the thing I didn't like about it was that you couldn't use multiple wavelengths with it very easily. And in a little while, I'll tell you why I really want to do multiple wavelengths. You couldn't do white light interferometry, and in a while I'll give you some examples of why I think being able to do white light interferometry is so important. And the real problem here, if we look at the system, well, you have these wave plates in here, but you can make achromatic wave plates, so that wasn't the real problem. The real problem is you have this holographic element. And so if you change the wavelength, these images are at different locations for different wavelengths. And so you just couldn't use it with multiple wavelengths. You couldn't use it with white light. And so we had to come up with something different. And so that leads me to the last topic in this section, which is the following. What we're going to do here is we're going to come up with a phase shifter, which we've seen before, in fact, but we're going to see a use of it here, where the phase shifter is going to be, the phase shift is going to be independent of the wavelength, and it's going to be able to work with multiple wavelengths, so it's going to work with white light, and it's just going to be a simple little thing that we put in front of a detector, and we're going to get all our 4 phase shifted frames at once. And it's based upon an old idea that we actually talked about in class 2 or 3 lectures ago, where we said that if our test and reference beams have orthogonal polarization, and in particular we want one to have left-handed circular and the other one to have right-handed circular, we said that if we send these through a polarizer, we'll get interference, assuming these are coherent, we'll get interference. And we said that the phase of this interference pattern depends upon the orientation of the linear polarizer. And if I rotate this at an angle alpha, the phase of this interference pattern will change by 2 alpha, independent of the wavelength. So this is a paper on this, and if you go back and look in literature, you'll find papers that describe this long before this. But I like this particular paper because they're talking about having achromatic, in making a left-handed and right-handed circular, use a quarter wave plate, and they talk about using achromatic quarter wave plates. They also point out that these beams don't have to be perfectly circular polarization. They can be slightly elliptical, and nothing real bad happens. So it's quite a nice paper here. So what we're going to do is the following, and this is something that you've only been able to do the last few years, and that is to make a very small array of wire grid polarizers that work in the visible. And so if I think of this array as being made up of unit cells of 2 by 2 elements, where we have wire grid polarizers here that transmit, angle I guess I use here is 0 degrees, 45, 135, and 90. So if I take these 4 unit cells, I have my 4 phase shifted frames. If I look behind these four little micropolarizers. So we're going to make up a grid of these wire grid polarizers using lithographic techniques. And you're going to make this up so the size of these polarizers is the same as the size of the pixels on your CCD array. And so I'm going to take this little array of polarizers and put it right up against my CCD array, where in front of each element, each pixel in the CCD array, I will have a polarizer. And if I look at a group of 4 here, I will have my 4 phase shifted frames. Now I'm losing a little spatial resolution here again, because I'm using 4 elements to get 1 data point. But now you have CCD arrays of millions of data points, and so it doesn't really bother you so much to use 4 to get 4 pixels to get each data point. And these work well over the whole spectrum here, quite well. So you just bond this array directly to the CCD. Now I have one more picture of this array here, and now I'm going to zoom in using an SEM, zoom in and just look at the 2 by 2 element. And so it might look something like this. Okay, so 4 phase shifted frames behind this. Again, these have to be the size of the pixels of my CCD array. So we have to have our interferometer here where the 2 beams have orthogonal polarizations. And in fact, we want a left-handed circular and a right-handed circular. And then my detector here, and then bonded to the front of the detector, I will have my polarizer array. And this showing that you could have different configurations here of the polarizers of 0, 90, minus 90, and 180, or 0, 90, 180, and minus 90. Doesn't matter which way it is. And so this is really made up of a bunch of, I'll say, A's and B's and C's and D's. So I just take my, come back here, just take my polarization interferometer here, adding a quarter wave plate to the output here, and putting my little polarizer array on my CCD. And if I look at all the A elements, I get this, and the B's, and the C's, and the D's. So I'm getting my 4 phase-shifted frames at once. And it's going to work very well in the presence of vibration. And I can change the wavelength. I can use white light. We'll show some results for that later. But and it's still going to work very well. So any questions on how this works? So this is what we're now doing at 4D Technologies, making this type of interferometer. Well, what I want to show now, if you don't have any questions, I want to just show some results obtained using an interferometer of this type. And the first one is measuring vibration. So I said we can take data in the presence of vibration, but if I have a surface that's vibrating, I can also measure how the shape of that surface is changing with time. And so we set up a little example here of here's a little plate, and it turns out this is a platter from a hard disk drive. So it's just a little metal plate. And we mounted a PZT on it that is going to cause it to vibrate. And we can change the frequency of the vibration. And then we're going to set up our interferometer just to look at this to see how the shape changes as it vibrates. So first, without vibration, this was the surface. I mean, it wasn't flat by any means here. And so showing the interferogram and then showing a little 3D map of what the surface looks like. Now, this plate was found to have several resonant modes, 55 hertz, 407 hertz, and so on here. And if I look at it at, well, I guess it's actually 408 hertz. I looked at it here, or we looked at it. And this is taking a few measurements as it vibrates. And you can see what the shape looks like as a function of time as it vibrates. Okay, so this is looking through one cycle of the vibration. Or, if you want, you could make a movie of it vibrating, and I'm going to show movies for different frequencies. First one was at 55 hertz, and it just tipped and tilted. The shape didn't change much other than tipping and tilting. 408 hertz, we got a mode that looks like this. And so you can measure this thing quite nicely as it vibrates. Change the frequency from 408 hertz to 3069, and the shape changes more. But you can make quite a nice measurement of it. So this shows that you can take a surface that's vibrating and measure just how the shape changes. And this is just another mirror that kind of like these movies, so I picked this one out too, of a deformable mirror. And this is looking at how the shape changed as we deformed it. And another deformable mirror here was a 32 element deformable mirror. And this looks at how it works as we actuate different elements in the mirror. And then here's another one. This one is 32 by 32 elements, I guess. So again, you can measure how it works. And then this one is my last one, and in some ways my favorite one. This was actually taken in a classroom here at the university, where we set up one of the interferometers, and one of the students had a cup of coffee. And so we took the cup of coffee, and so here's the top of the cup, I guess. And you can see the heat waves going up into the beam. and you could measure how the index, or the optical path difference, varied as the heat waves came up. And then the picture over on the right is just, once you have this data in a computer, you can play with it, and you can find the slope, for example. So this is the magnitude of the slope of the OPD variations. So we've looked at several different ways of getting around the effects of vibration. And I really think that these single shot approaches are the best. Some people like it where you put in a lot of tilt fringes and you do a Fourier transform to get the wavefront. Some people like the spatial fringe technique where you put in tilt to get 90 degrees difference between adjacent pixels. My preference is really the last one we talked about, but all these techniques work fairly well. But the conclusion you come to once you play with these dynamic single-shot interferometers, and they're all fairly new, you really can get around the effects of vibration. You can do testing in environments you never could have dreamed of working in before. Real manufacturing areas, you can get data. You can test large mirrors this way without vibration isolation. Air turbulence is always a problem. You just introduce you have air turbulence. You just measure the data a lot of times and average it out. And you want to have a lot of air turbulence. So sometimes you actually make it worse by putting fans in the system to really stir it up, and then the averaging works even better. Things like we're talking in this last class about the double frequency errors that come from the phase shifts not being 90 degrees. You know, this is actually a good way. Having vibration is actually a good way of getting rid of these double frequency errors, because you have enough vibration, and then you just average a lot of data frames, and you average out these double frequency errors. And so we've made interferometers where we actually have added a little vibrator in the interferometer to get to cause more vibration, so you could average out the effect of the double frequency errors. You can make movies of showing how the surfaces are vibrating, seeing how the shape of the surface changes. And it's really true that, you know, once you get used to using these dynamic phase shifting interferometers, it's hard to go back to work with these temporal phase shifting interferometers. I think, you know, at the present time, there's certainly many more temporal phase shifting interferometers out in the field. But I think if we go ahead, 5 years from now, I really think the dynamic ones are going to be replacing the temporal ones, because they're just easier to operate, and you can get better results. So any questions?
Yes, in terms of cost.
Oh, you mentioned a bad thing here, cost. Yes.
For instance, like the holographic polarization and the array one, which one is more or less?
Well, if you go to, I think right now the dynamic ones, regardless which one you pick, it's going to be more expensive than temporal ones. I think that will change over the next 5 years as we get, as we and all the competitors out there get better at making these. Which one is the least expensive? There's not a lot of difference. Once you get to the dynamic ones, the differences in cost depend upon aperture size and maybe the wavelength you use.
What's a ballpark of how much an interferometer?
You're talking about $100,000 plus for each one. Temporal phase shifting, I mean, these prices used to be $100,000. They're now maybe $40,000 or some lower than that in cost. Again, it depends on apertures and accessories and so on. But there's probably a factor of 2 in the cost right now. But that will, competition will drive that price down. Yeah. Any other questions? Yes, you can do the polarization in the Fizeau. It's more complicated, but I'm going to show that in, I think it's the next section, that will show a way of doing it. It's more complicated because the two beams have to have orthogonal polarization, and the Fizeau is more common path. Two beams are not so separated, and so it's harder to do. But we'll figure out a way of doing it in the next, I think it's the next lecture we'll show that. Any other questions? Well, I think I'm going to stop here. I have a little more time, and I could go on. The next section is non-destructive testing using phase shifting. And then I'll realize it's a section after that that's going to have the Fizeau in it. I would start this section here. I guess you can't see it. But I'm going to stop at this point because if you go back and look at the schedule, well, where I'm supposed to be at the end of this lecture, I'm supposed to finish section 5.5, which is what we just finished. So I'm exactly on schedule. And so I think I'll stop here. I don't want to get ahead of schedule again. And so I'll stop at this point. And then when we come back Tuesday of next week, next class, we're going to talk more phase shifting, and we're going to talk about non-destructive testing, phase shifting. And then after that, we're going to talk about multiple wavelengths and white light phase shifting interferometry. So thank you for coming, and I'll see you at the next class.